Hey guys. So my name is Krunoslav Zaher. I've been working on RxSwift for the past approximately 3 years. And we've also created RxFeedback. And I'm here today to tell you more about how we are using Rx in more stateful environments like iOS applications. So that's the title of my current talk. So why did I use the words like modern and architectures when RxSwift is just 3 years old? Well, the broader kind of reactive community is a bit older, not much. So there were these kind of common patterns that you could find online, how you would use them. And we find that these kind of patterns didn't work for us the best. And lately, a lot of libraries are appearing that are kind of similar in one way that they're using more coarse-grained state. So RxFeedback is one of those libraries. There's Redux Observable, ReactorKit, some other ones. I'm going to talk to you today about RxFeedback. There's an assumption that you know at least something about RxSwift, or at least have some basic information about it or some other reactive libraries. So why did we actually do all of this? If you are using some kind of reactive libraries, you'll actually find it pretty straightforward to use for networking and in some kind of stateless environments. What you're doing is just .map, .flatmap, .map, things like that. It works out pretty well. There are no issues usually, straightforward, it works. Nothing really interesting there. But then you have something like this. So if you've ever worked on some kind of app, you've maybe run into issues when you have cyclic data dependencies. So please don't try to understand this code. This code is my code. I'm sorry for it. I've written it 2 years ago. These were kind of some of my earliest attempts how to tackle these kinds of issues. They aren't pretty. I wouldn't be here advocating you doing something like this. So we've learned a bunch since then. So I'm going to tell you how would we actually solve these kinds of problems right now. So let's say you have some kind of standard problem that has cyclic data dependencies. For example, you're working on an app that uses some kind of paginate API, so you're performing a search, and you know that when you scroll to the bottom, you'll need to load kind of the next page, and then you scroll again, you load the next page. Well, there is kind of a circular data dependency there, because if you're, for example, using, GitHub API, you get a URL of the next result set, and it's stored somewhere in some state. Then you use that URL to make an API call. Then you get the new URL, and you somehow have to replace it with the old one. So that's kind of a cyclic data dependency there. It looks like a lot of problems actually are really similar to that one. So what I would now do is I would just create a high-level description of the system first. So this is a struct that describes the scenario. You have a query that you've entered in some text box. You have results that represent the current fetch results. You have URL of next page to load. And should you start loading next page? And you'll notice that this state basically contains description of everything. It contains the view model and description of effects, basically everything. So on the bottom of this screen, you'll see something we call state queries. If you're using something like RxFeedback and you're storing your state in a database, then you'll use normal database queries. If you're using some kind of struct to store your state, then you'll use some kind of calculated properties to pull out the interesting data from that struct that controls the loading of next page. So, if you look at this code, I think it should be pretty easy to understand most of it. To a lot of people, it's just plain Swift code. You don't need to know Rx. You don't need to know anything. It's pretty small. But how do you actually perform those queries? How do you actually do it? So this is actually how you load the next page. So please don't forget that you have no idea at this moment what is a feedback loop. Just don't think about it. I'm right now going to just demonstrate that this code is really readable, and after that, I'm going to explain you what it really does. So how do you read something like this? Okay, so there is something that creates a feedback loop. So there is some kind of feedback loop factory, and we are creating a feedback loop that reacts to this query. And this query can return either a nil, you see the query on top of the page, or it can return a URL that you need to load, okay? And once you have that URL, then you load it from through some API, and once you're done loading it, then you map it to an event that says, okay, I've loaded this data, and I'm done. And then you return that data to the feedback loop. So this is the basic structure of all of the feedback loops, more or less. And I'm hoping that you were approximately being able to, without even knowing anything about RxFeedback, kind of understand what's happening here, right? So now I'm going to explain you how this actually works. So this is the basic structure how RxFeedback looks like. I mean, if you don't have state, then you don't have a problem, right? Then you're doing just map, flat maps, and things like that. So you obviously need to have some kind of state. It's a really good idea, and it's really useful to put all of that state in one place. So that's kind of the big green box there. So on the bottom, you can see basically what are feedback loops. Feedback loops are just lambdas that take that state, observe it, and after that, depending on that state, they perform different side effects. For example, you could be doing UI, so you could be using that state to map to UI and then observe events on the UI. You could control some timers. You can communicate with Bluetooth layers. You can do some networking, like really any kind of effects. And the result of effects produce events, and that events mutate the state. So I'm sure you've seen similar architectures like this before, right? So this is kind of both an architecture and an operator. So if you're using this like some kind of architecture and you have a really large state, you can store that state in any kind of either relational, live database, or anywhere else. And then you can use those queries to kind of observe that state. Or you can, if that state is manageable, you can use just the system operator that I'm going to present a bit later. So this is the public interface of system operator. So why did we create a system operator? Well, the reason is simple. In RxSwift or any other reactive library, there really isn't currently, as far as I'm aware of, any operator that enables you to model those circular data dependencies. So yeah, we've just created one. So this represents this kind of entire system. For you to be able to define this programmatically, what it does, you obviously need some kind of initial state. You need to tell the system, OK, you start from this point, from this state. Then you need a reducer that combines the events and state. If you've ever done, like in regular Swift, array.reduce, you might be familiar with the concept. It's exactly the same. And there are obviously those feedback loops that represent how do you do effects depending on that state. And this is the format of feedback loops I've shown you before. It's a little bit of overwhelming, probably right now. But you can check everything in more detail in a GitHub repo. OK, so this is kind of how feedback loops work. Remember that first feedback loop that I've shown you previously? So this is the good thing is that there are like more than 90% of feedback loops have exactly the same pattern. And this is basically we've named it React. We could have named it anyhow. So what you're doing, you have a query upon state, and that query returns something that is nullable. In case the value that you are returning is nil, then you kind of intuitively assume that you really shouldn't be performing any side effects. If the query able to return some value, then that value is passed to the effects lambda, that really describe what you're doing. If you're doing some kind of network API call, you get a URL, and you just get an observable that performs those events. And basically, after you've done with them, you produce an event. So this is kind of a really, really, really common feedback loop. We use it probably more than 90% of time. The other one that's really common is when you want to bind the state to the UI and actually observe the UI events and mutate the state that way. It's kind of similar to this one. I'm not going to spend a lot of time explaining to that one. You can just check it in the repo. So these are the two common cases that actually cover like really probably 98% of all of the feedback loops you'll ever need in your app. And you can always, if you like, build one manually, but there is no need to do that. So yeah, this is like you're taking data from query, passing it to the effects lambda, and doing the side effects you need. OK, so one of the questions that we get a lot is like, does this perform well? Because you're putting all of the state in one place. There are also some other architectures that are doing this. And yes, so far we haven't encountered any performance issues. If we have a really, really big state, we just put it into a database. In case we have a small state, then we are using that system operator. And even if you run into some kind of performance issue, there are like standard Redux tricks that you can do to improve performance. But like I said, we've never actually run into some kind of performance issues, especially on kind of today's hardware. So one of the questions is, how does this differentiate from like Redux and Elm architecture and things like that? Well, one of the differences is that we are using part of the state to describe actually what are the current effects that you need to be executing. Another part is that Elm and Redux have an assumption that there is necessarily a view that you're observing that state. And so, for example, in Redux, you have some kind of middleware that is between view and state. But what if you don't have view? And it turns out that in some cases, we actually don't have any view. So that doesn't work for us. For side effects, what Elm does is I think that it has additional return value from the reducer. So it's a bit different from both of those. The other difference is that Redux and Elm both have this kind of really big state that you need to have application level. So you can also do that with RxFeedback if you like. There shouldn't be a problem if you manage to somehow figure out how to conquer the navigation controller and things like that. But you can also use it to more fine-grained approach. So you can have like that state per view controller, and you can just update that state per view controller, so you don't have to constantly push your changes through entire application state and basically do a lot of kind of that boilerplate code for you to be able to propagate events for some view controller. It works out really well. OK, so the next thing is, from this diagram, I don't think that anybody can actually figure out like what is the percentage of code in each of those parts. The really important thing is, and we've proved that empirically, basically that for state and events that are pure Swift code, it's approximately about order of magnitude like 5% of your code base. And that is really, really small. So that small Swift code actually contains like really high level abstraction of your entire system, and it's really easy to read it. Basically, I spend probably 90% of my time reading someone's code, so this is extremely helpful. I only need to study 5% of the code, and I know all of the things, what it's doing. And feedback loops are basically like 90% because you have a bunch of really kind of boring boilerplate code where you need to map to UI, you need to do adapters for networking and things like that. But those are kind of implementation details you usually don't care much about. And you can easily find like where is the feedback loop that performs the effect I need. So one of the benefits of using this pattern is that it normalizes architecture across the team. I'm not sure if you've used any kind of reactive library in team environment. Usually what happens when you have some problem, if you have 10 people, you'll have 10 completely different solutions. And I'm not kidding, like completely different. And that's bad because when you go to your teammate, when you're doing code review, it's not easy to figure out what was their mindset, what were they doing. So this makes the code base far more consistent. And since you have that small state, it's really easy when you're doing pull requests, figure out what your coworker is trying to do. And everybody kind of have the same agreement how they are working with effects. And you can even create a cookbook. So if it's a state, then put it into a state struct. If it's a way to change state, create an event. If it's an effect, then just create another feedback loop for that effect. Another benefit is that I've noticed a lot of people, when they face kind of those cyclic data dependencies, and they're really, really, really common, the way they solve them is that they make subscription calls. And I'm not going to bore you with that, but if you're doing a lot of subscription calls, you're probably using Rx in an unoptimal way because you're kind of leaving the monad and you're hurting some of the compositional properties of the library itself. So this solves a lot of also those subscription calls where we are trying to help people how to use Rx in a more idiomatic way. This is something that's usually an afterthought, but it's really important in mobile apps. I mean, if you're working on a web page, then the assumptions are a bit different. So if you have some kind of background process in your app that's really long-lived and long-running, what happens when a user closes the app, or the app crashes, or you have some other problem? You would usually expect when the app restarts that all of that work is kind of resumed automatically in the background. If you are using RxFeedback, then you have written serialized events, and basically you're just resuming. There is no extra work. There is no extra code that you need to put in. There is also one small thing that probably no iOS developer that I know is working, but it's really simple to do with this. So it was probably important more previously when you had really resource-constrained devices. When your view actually leaves the visible area, you should stop spending CPU time on it. You can just store the state of the system. And when you navigate back to that view controller, you can just continue where you left off. There is no reason why you should, in background, observe some expensive resource and things like that. So this gives you actually really nice properties regarding that. For us, it's more important because of that first dot, actually. This is really awesome for testability. Like you've noticed, I mean, Redux also has kind of similar properties. You can test the reducer. You can test those calculated properties on state. You can really easily, feedback loops are a way to do dependency injection. So you have really separation between the high-level abstract representation of your system and dependencies that perform those effects. And you can either mock those feedback loops inside your unit test. You just create a lambda, or you can use the same functions and mock the resources in some other way. It works the same. But we actually go a bit further. So this is kind of typical example of the code that one would write. For example, when you're fetching something from server, you're observing some kind of text box and query. It doesn't matter what reactive framework you are using. It's about the same in any of them. So there are two ways that you can change the operators. You can put observe on the outer sequence, or you can put it on the inner sequence. So one of these is actually wrong, and you can get stale data. So the first one is actually that I've seen people most use, but it's wrong. Because what happens is that after the cancellation logic, you have an event that could be enqueued on the main dispatch queue, and you could actually receive that stale event. The correct is the second one, because even though this is enqueued, the cancellation logic will properly be able to cancel the event if query changed, so you won't get any stale events. So if you're just using, you aren't thinking about any of this, you're just using the code that we've provided, we've handled all of these kind of edge cases for you. It's like no-brainer. You really don't have to break a sweat and think about these things. Another really big topic that I'm not sure why nobody's talking about it in reactive community or anywhere else I've seen is reentrancy. So this one will probably bite you when you have fairly complex app, and that's probably the most worst time when you start to think about things like this. So there's like Wikipedia definition that you can check, but this is just a simple example how you can create reentrancy issues. You have some kind of state, you're observing that state, and when new value arrives, you immediately change the state. So this state fires a new event, you send the next event, and this will probably crash with Stack Overflow after, really soon. Or you can have things that have partial problems like this. This is basically what reentrancy means. If you're using Rx in debug mode, then we'll display this message that we've detected that something is funky happening with your system. If you can also replace the message with a crash if you like, but that might be a bad thing to do in production environment. So why is reentrancy problematic for reactive libraries, like for all reactive libraries? They all work with something called basically observable sequences. And observable sequences have an assumption that there is an ordering between elements. So if you have an element, and while you're processing it, it takes some time. And if you receive on the same thread new element, like how are these elements ordered, it's not really clear. Like what should you do with them? The way Rx handles this currently is basically we try to do the sanest thing we can, but it's not possible to cover every possible edge case. So the best way would be just to avoid having reentrancy problems at all. If you like, you can change the behavior and crash the app in that case, but proving that your app doesn't have reentrancy cycles is really far from trivial. But we can't do it for your entire app, but we can prove it on the level of system operator. So the way that system operator is designed, the way these kind of feedback loops are designed, that even if you would normally have reentrancy issues, we handle that internally for you correctly, and in a way that doesn't really kind of negatively affect those kind of cancellation guarantees and things like that. So this, I'm not sure, I'll highlight. Basically, I've just taken that feedback loop you've previously seen that takes some data from an API, and I've changed it with something that just immediately returns a value. So when can this happen in a real-life app? Well, if you have something cached, you can immediately read something from cache, return it, and if there aren't any special methods of handling these cases, this will immediately cause the reducer to run, you'll get a new state, and you could run into issues. So this React feedback loops actually handle all of these kind of edge cases for you. It's a no-brainer. So you just use it, and it works perfectly. There's like really, really a lot of other benefits, and we find them basically every day. I don't have time to actually go through all of them right now. You can check out the repo. You can find approximately how are we using this concept there. You can find a couple of examples. And you can mess up with the code and see how this concept works. And that's it. I'm hoping you'll have some benefit of this library, or at least hearing all of these things. Yeah, thank you very much.